Okay. Yes. So you can ask. You should ask the questions that you have. Sorry. So what are we asked to prove? So this is what we are given. Okay. And what are we asked to prove? Prove what works. No. So the sequence works, meaning there some like what is it that we have to prove? No, but proving a sequence is what does it mean to prove a sequence? Is there something about the sequence that you want to prove? Is there some formula which you want to prove, or but what works? Uh, so do you have the reference for this? Yeah, so just have a look because I don't know what is being asked to prove. I mean, is this something that is, let's see, given or? No, but what holds true? You mean this? No, but okay, so this is the rule, but this is the rule for what? I mean, I could just say this rule and then like then that is a statement, right? I mean, it is. I mean, it's a sentence, not just. I mean, it is given. Then I don't understand. Like, if suppose the first number is 1 and the second is 1, so let's say that f1 is 1 and f2 is 1, then f3 will be 3. Sorry, 2, right? Just putting the values. F4 will be 3 and so on. But then what is it that we have to prove? Okay, so what is the reference for this question? Oh, you sent me on the mail? Oh, so it is in the Meet, Google Meet? No, so where have you sent the link? No, I have not yet received. Now I've received. Okay. Hmm. So where is this question? Example number? Some example number or? Oh, but in the, okay. So let me share that screen. Let's share that tab. So it begins with, you may have heard of Fibonacci numbers and they occur. So this recurrence that you see, right? There is nothing to prove in this recurrence, right? Because we are saying that my sequence starts with 1 and 1, or 0 and 1 in this case, right? As f0 is 0, f1 is 1. And then I build the next terms using this rule. So there's something that I'm saying and declaring, right? There's nothing to prove in that, right? You understand, right? I mean, I'm declaring that my sequence, my list follows this rule. Okay, so there is nothing to prove here, but obviously there may be some other process that may be given to you, and there they may ask you that, look, this process on the nth day, what happens? It's connected with the previous 2 days by this rule, but then you have to, from the process you have to work out and establish this fact. But here it is being declared that, look, I'm starting with this 0 and 1, and I'm using this rule to move forward like this. Okay, so then there's nothing to prove, right? So far. But then let's have a look at these things. Okay, let's try to show this, right? Example 3.6.1. Maybe have you tried to do these examples so far? Yeah, so there is nothing that is asked there, right? So let's try a few problems from here, right? And then maybe the rest you can try on your own. Okay. So yeah, so let me share the screen and let's try it there. Yeah, so this is the rule for the sequence. So let's take F1 to F2, so on. And let's say that, just trying to prove what they asked, show that Fn is less than 2 to the, and this is a useful fact you can imagine. So let's try this. Yeah. So this is true for all n. So again, this is what we are given, right? That my sequence is built up using this rule. And we want to say this fact about the sequence, which you can see is true for the first few terms, right? Or maybe less than or equal to is better. Or it's correct to say less than. Yeah. So let's try this. I had also sent one screenshot from Arthur Angel, which also had this Fibonacci questions some time back, I think. Either ways. Right. So what happens for n equal to 1? F1. So F1 is correct. So that's fine. Yeah. We need to show this is true for all n. So we want to say that F10 is less than 2 to the power 10. Without really calculating F10 explicitly, we want to be able to say that, right? F100 is less than 2 to the 100 without actually calculating F100. That's a good thing. We are proving that, or we are assuming that? Okay, right. So let's assume. Yeah. So again, that's induction. So let's assume that it is true for n equal to k. So let's assume that fk is less than 2 to the k. Nice. Okay. So can we use this alone to show that fk plus 1? So can we use that to show that fk plus 1 is less than 2 to the k plus 1? Okay, so then what should we do? Let's see. Yes, you're right. It seems yeah, it just seems like you cannot do it with just that. So then what should we do? We do, sorry, I don't understand that. No, but you said that we cannot prove that with just what we have assumed. Right. Yeah, am I right? I mean, that's what we have to prove eventually. Yeah, that's what the whole question is. But should we assume anything more, or how would you show that? So just how would you show that fk plus 1 is less than 2 to the k plus 1 using for fk? Oh, you know that fk plus 1 is fk plus fk minus 1. This is what we know. This is the definition of the sequence. Okay, so no. So you know that fk plus 1 is equal to fk and fk minus, right? Sum of these two things. You would like to show that this is less than 2 to the k plus 1. So what do you think we should assume? We already know that this is less than 2 to the k. Well, it is the natural thing to do is to also assume that this is less than 2 to the k minus 1. I mean, this seems to be the only natural way, right? The most natural way is to just make this assumption, and we can make this assumption, right? As we have discussed, I mean, just here, it seems to be a necessity, right? That you cannot just assume one step back, but two step back, and it's all makes sense, right? There's two-step recurrence and so on. So we should assume two things. Now, can you work it out? Let's see. So I'm just erasing this so that you just work it out for yourself first. So now again, we are assuming two steps back. We're assuming the statement, same statement, but for two steps back, not just one step. So how do you club those assumptions to establish this for fk plus 1? Yeah, I mean, you could take some concrete things and try. For example, if you assume that this is this and f11 is this, use this to show for this. See, f10, the 10th term is less than 2 to the 10. 11th term is less than 2 to the 11. Use them to show that the 12th term is less than 2 to the 12th. You could try that. Yes, because that's what it is. Exactly, right? So f12 is equal to, because it's just both of them combined. And this we know is less than 2 to the 10 plus 2 to the 11. But obviously this is less than 2 to the 12. Right? Because you could establish the, how would you explain, let's see, how would you explain that this is true? No, I'm just asking about the number thing, right? That is over. No. This, so let's leave the k, right? We are doing this for the numbers first. You can just write k's in those places. So what I'm just saying is that we are trying to just do for numbers. So f10 and f11, and you said like just club them, just combine them. So then we combine them and we get that f12 is equal to f10 plus f11. Okay, and this is less than 2 to the 10 plus 2 to the 11. That's our assumption, right? Now, how? So my question is, how do we show this? Just that last thing. Yes. So why is it less than 2 to the 12? That's another thing which we need to show, right? So you want to show that 2 to the 10 plus 2 to the 11 is less than 2 to the 12. It's something that can be checked, but we would like to show it without actually calculating those numbers. So again, for now, we just forget about the Fibonacci thing and just try to prove this, because this is the key ingredient. That's the last step. Right? Sorry. Yeah. So this is something that you have to think, right? Now we have to think about this. So this is a problem that we need to do. Come on. So this is something that we should try. I mean, this is just an inequality about concrete numbers mostly. Just think, I mean, so you know that 2 plus 2 square is less than 2 cube, right? Yeah, so this is something that we know. How do you use this? How do you build this to this? And then how do you show this? See, the easiest way should be, let's think. Let's take some more time and think. Let's try. Sorry. Okay, what does that mean? Like bases. The bases are already two. So what? Hmm. Yeah, we are comparing. So ah, right. One just a second. Yes, that's right. So you're saying 2 to the power 10 can be written as 2 to the power 11, sorry. Okay. So then how do you use this? No, so I didn't get this. So say so far is okay. So then what do you do next? So you are in the right direction, right? So you're writing 2 to the power 11 as this. So you're kind of making a more similar base. But then what do you do next to show that this is less than 2 to the 12? Right? That's what we need to do. Yes, so any ideas? Let's see. Yes, try. That's right. So we know like smaller numbers would mean like we know this, um, we know this, then we know this. Yes, it did it not come. Oh, so that's why there's a lot of confusion. Okay, so I sorry. Yeah. I didn't share the Zoom thing. Okay, that's why is that the reason why there is confusion? Let's see. No, so not this. Can you see now? No, you cannot. It's just yeah. So I've been writing these things. Sorry, that's bad. Yeah, sorry. Right. Yeah, but why does that rule hold? That's the question, right? Because I mean, it's not always true that all rules that start to hold will continue to hold. That's not a, there's no such thing, right? So why should this rule continue to hold? And you have almost done it in the sense this thing, you can use this also, I think. This 2 to the 10. Yeah, so how would you club it? Just take this common, and when you see 2 to the power tens, they one thing that you can try is just to take them common, right? And then you get this. So can you say why this is less than 2 to the 12? I just took the 2 to the 10 common. That's one natural thing to do. When you see 2 to the tens, one natural thing is to just take 2 to the 10 common. There are other things you could do, but now can you say now why 2 to the 10 is 2 to the 10 times 3 is less than 2 to the 12? Yes. So it's less. So this is just like that, right? I mean, and also what you could have done is just, I mean, see, when you have to prove inequalities, you can just take things common from both sides. Right? I mean, so if you look at this inequality in front, you can take just, you can simply just take 2 to the 10 common from both sides and just cancel it, right? You could cancel this because that's a reversible step, right? Which is obviously true. Is that okay? Right? I mean, this is the, so this is what I mean when you see inequalities with a lot of terms similar. The easiest thing to do is just to cancel the common things and just see if it still holds. Obviously, cancel the positive things. I mean, that will be positive what you're canceling, right? Or you could just say, okay, I start with this and I multiply with 2 to the 10 on both sides, and you get this. It's just inequalities, right? Cancel them, or just build it up from. Okay, so we know that this fact is true. Now that we have shown the case for 10 and 11, like assuming it for 10 and assuming this shit for 11, we're able to prove for 12. Now I would want you to tell me the steps, how you would do it for k. Let's work this out because we want to get used to these things. Then you will see that it's very easy once you just get a hang of this little bit. Yeah. So now let us try to do this. It's just essentially the same thing, but I want we to just to be, we should be able to write it clearly without any hesitation. Okay. Yes, the inductive step, right? I mean, what we did was what we have to do again, but what we did was for 10 and 11, we not just need to do the same thing for k minus 1, and build it up for 2k plus 1. So what we did was for specific numbers, right? 10, 11, and proved it for 12. This should be less than. No, so say that more clearly. So it's less than what? Yes. Okay. And then this is what we have assumed. So you added them just like we did for the. That's good. Now what's the next thing? Right. That's right. That's good. So we are almost done. this is, so finally we need to conclude this. So I know that we are almost in. I'm maybe focusing too much on the details, but we should just, yes, exactly. Right. I mean, yeah, I know this is almost done, but just to write the full thing, right? And this one should mention that this is f of k plus 1, right? This fk plus fk, that's obviously, but just to write it. And so we are done. Okay. See, the steps are not difficult, but it's just that we are not used to this way of method of proof writing. And so we have to hands-on do these things. And it's, but I hope you appreciate the power of this method, right? Without actually calculating, we are able to show this fact, which is not a difficult fact. In fact, much more is true, but that's okay. We are able to show something, right? Without actually calculating, you know that this is the, yeah, and then you can comment on the number of digits after some time. You can comment on a lot of things without actually calculating them. And so that's the good thing, right? Okay. So we are, so whenever things are given via patterns in this way, induction is a good thing. But let's actually do more problems like this. It's good to do easy things, but it's just good to do them, yeah, clearly. Even if they're easy, that's not a problem. That's a good thing to do it. Okay. Let's try. Okay, so let me just maybe give a, let's try this. Okay. Let's see if we can do this. Show. Okay, just 1 second. So there is something incomplete here. Do you see anything incomplete in this? Just go through the entire thing and see if there is logically anything incomplete. Just take your time and think. Is it complete logically? So we assumed something and we showed the next step. That's good. But do you think something, so just making the question more specific, do you think something in the base case is missing? Right, right. So when n equal to 1, so something is off. So we need to make that, you need to make that more precise. Something, so even for f of 1, we don't need to prove because we are kind of showing it directly. But f of 2, also, we don't quite have our hands on. We don't have f0. Yeah. We should, so base case shouldn't be 3. Okay, what I'm trying to say is, so why do you think base cases should be 3? Let's think. Yeah, so you're saying it's just kind of the right thing. Yeah. So, I mean, think about this. So what you have said is almost the same thing, and tell me if it makes sense, is that we cannot prove this fact for F2 by induction. Right? Because you see, when you try to prove for F2, you end up with F0. You end up with needing F0, which is not there in our picture here in this definition. Right? So we should say that, okay, let's just check F2 explicitly. Right? So why are we checking F2 explicitly? Because, well, there are many ways to see it. I mean, you saw that there is a problem because you come to F0, and that's good enough of an obstruction to realize that you should just check it, and it's just easy to check. It's there, right? You should just check for F2. Logically, what other problem could happen? Well, because you cannot prove it, as you said. Another thing, another way in which one can spot this is, okay, when I'm proving it for fk plus 1, I am needing the previous two statements. And so I think that's what you're also saying, is that when you start to prove it for f3, you will need the fact for f2 and f1, right? And so you need to assume those two things, because again, for F2, you cannot prove. So when you're using previous 2 steps or previous 3 steps, then you should prove those previous 2 or previous 3 steps, right? Or rather, you should start with proving some 2 steps or 3 steps, right? Depending on how much you're needing. Okay. Is that, yeah, that's, and that's a subtle point which we had also discussed in the first class, but now we can see it in action. I mean, if you miss this here, then it could happen, but anyways, it will not happen in this case. I think that you end up proving a wrong statement. Okay, but anyways, one should logically. This is a very small. I'm just nitpicking, but we have to just know these, learn these things. Important to avoid the fallacies of this. Okay, because with new tools, there's new possibilities of creating these fallacies. Anyways, so but it's just trivial to check that it is obviously true. So we just check. All right. Yeah. Okay. So now, as I was going to say, is let's try to just take the same result, and please try the other problems in that page that you had, right? Try the other problems, but I'll try as much as we can today. But yeah, it's, I think, good to do these problems explicitly in front, so that we see where we are getting stuck. We say wrong things, right things, then we learn, right? Otherwise, you don't know. So let's see. So what I am thinking is, can we show this? Let's try this. Yeah, I mean, it's not needed, I think, but I'll just put this, though I think it's not needed, but it's just putting it there. So is this better? Because see, what we showed earlier, let's just have a look at this for a minute. What we showed is this, but now you would notice that this is less than 2. Just check this first. Yeah, root 5 plus 1 by 2 is less than 2. That's correct. Yeah. So how much is root 5 roughly? I know it's correct, but how much, just asking, how much is root 5 roughly? Certainly more than 2, but and also less than 3. Certainly. Yeah. So that's right. That's and it's less than 2.5 also. But anyways, yeah. This is true, but then what does that mean? It means that this is true. So earlier we showed that the Fibonacci numbers, the nth term is less than 2 to the n, which we showed. But now we are thinking of trying to show this, which is a more accurate statement. So do you agree? Do you see why this is a more accurate statement? Sorry? Yes, yeah. If we end up proving this, then that will imply that 2 to the power n thing also. Right. So this is a more accurate thing, right? It's a more closer thing. So it's in fact less than this. So I mean, just to say this more, this, if we take this 2.5, then this is maybe 1.8 or something. I don't know, something like that. So it's better. It's a more accurate truth. All right. So now let us try. Let's see if we can do this. Huh? And you will see soon after when that why this root 5 plus 1 by 2 is there. It's a very important number. You may have heard of golden ratio and things like that. Yeah, you can. It's related to that, and yeah. Let's try this. So try to go for the same thing, same method, assume it for this, check for the small cases, assume for the small cases. Try the same thing and see if it works. Well, you won't know if you don't try. Just doing a few calculations. Right. Yeah. I was calculating the square of 1.9 wrong. Okay. Yes, Satya. So, have any ideas? Yes, yeah. So we need to show this for all n, right? And we'll use the same method. So as you have already checked the base cases, you've checked more than base case. So you've checked for F1, F2, F3, F4. Fine, that's good enough for the base case. But how do we run the same thing that we did? We need to assume for some k minus 1. Yes. Yes. So first of all, what is exactly that we should assume? No, not for all k. So you assume for some k, right? You can't assume. Right. You don't agree. If you assume for all k, then there's nothing, then you assume what you need to prove. Right? See, for some k. But again, just like we did in the previous question, this assuming for one step will not be enough, right? You need to assume for fk and for some fk minus 1. You see, we're going to use the previous two cases to build the next case. See, you see, everything is same about this problem and the previous problem. There's nothing different. Conceptually, there will be no difference. And why should there? Yeah, one should at least try the same thing first, right? It's the same method. Let's try, and if it works, then it's good. Okay. Just now, what do we need to show? So we need to show f for fk plus 1, right? So again, just follow the same thing about combining the previous two cases, just like you did earlier, and see. Right. Right. That's the definition. That's right. So don't be like these numbers should not offset you, right? Just follow the same thing. What so what if it is root 5 plus 1 by 2? It doesn't matter. Just do the same thing that you did. No, why should you? There's no need to do that. Just write the same thing, right? I mean, why don't we just write the same thing? We don't see if you don't have to calculate, we don't have to do any approximations or calculations in this. I mean, let's see, right? I mean, we can just write the same thing, right? Just the exact same thing we did for the case 2. And let's see, I mean, if it's needed, then the point is that we are getting a little uncomfortable with this number, but we should not. It is there, fine, it's okay. We don't have to calculate it, right? We just copy it and see. I mean, obviously, for it's more advisable to just write lambda in this, just the notation for that and do, but that's okay. That's just writing more than what is needed, but that's okay. They're not really, there's nothing wrong. Because if I just write a lambda, then maybe it gets more it's variable. So let's just keep it. Okay, what do we want to show? Well, our final thing is that we want to show this. Right, this is it. If you can show this. Now see, earlier what did you have? Earlier you had to show something like this. And we showed it by cancellation. Well, to show this, just do cancellation, right? Just do the same thing. We don't have to calculate anything in the sense of we don't have to calculate its powers. We don't know what k is, right? So just cancel. I mean, this inequality is the same thing as just cancellations. And then let's see. So this root 5 plus 1 by 2 will remain. And this will become 1. So what are we canceling? We're canceling root 5 plus 1 by 2 to the power k minus 1 from both sides. Because that's the smallest power, so it's easy to just cancel that. And then we are down to this. Right? I just cancel the highest powers that I can cancel, simply. Now, is this true? Well, you can just check by squaring that last thing. So just square that thing and check what it is. Right? So just square it and tell me, and then you can just check if it's true. So I may make one question like, is this clear? This is a very easy but a very effective method, right? Just canceling the thing and reducing it to the simple check. Yeah. Because if two things are, one side is bigger than the other, then canceling the same thing leaves that inequality. It doesn't change the truth. And also you can vice versa multiply and get to the previous thing, to the original thing. Now we just square this, right? Just do the binomial squaring. So this one will become what? It will become 5 by 4 plus 1 by 4, 2 times. Just squaring it again. We don't have to calculate the decimals, right? Just squaring it and checking, because we don't need to check the numbers. And then this thing is what? This thing is root 5 by 2 plus 3 by 2. What is this thing? What's the right hand side? 6 by 4 plus half plus root 5. Right? Is this true? Well, we can just check. So this is 3 by 2, right? And then 3 by 2 cancels. And then we are down to, I mean, so it will just be something that we can, yeah, so it is certainly true. Yeah, it is certainly bigger. Have I made some mistake in the cancellation? I think I have, yes, because it looks too good to be, I mean, yeah, I mean, we have got the right thing, but there's, I think, slight error, but yeah, one can just, the point is that it is a trivial thing to check and you can just check it. So this 5 by 4 plus 1, so this is 6 by 4 and this is 3 by 2. So that's okay, but then this is root 5 by 2. Now see something very interesting here. It's in fact an equality. If you do the calculations correctly, you see it's in fact an equality, which is fine, not a problem. But it is the exact same thing, and that's an interesting thing. That's a very interesting thing. You think about this, right? This is an exact. This is related to that, but exactly how that we can see, but later. Yeah, you can think this is the exact term. Okay? Now I would like you to try this. What if I made this 4? Or what if I made this 3? Do you think it will be true? And if not, or if, how would you? No, so I should make the question formal. Now I'm trying to make it more smaller. Okay. What I'm trying to do is I'm asking, is fk less than equal to root 5 plus 1 by 3 to the power k or n. You see, I'm trying to make it more smaller and see. Do you think it will be true? So you think and tell me. Let's see. So is this true for all n is the question. So I've made this more smaller. So I'm trying to get a better inequality and see if I can get. Let's see. Why? Okay, so that's your hunch, right? Now, how do we check this? How do you show that you are indeed correct? Yeah, so based on what we've done so far, it seems, and that was almost an equality. It should not be true for lesser numbers. Yeah, but then is it? But then you see, f1 is 1, and that is less. Is this true? It is true. So for f1, it is true. Okay. For f2 also it is true, but that doesn't mean it will be true. As you're saying, it should not be true. This is correct, right? Because root 5 is 2 point whatever, is more than 2. So you see, for first two terms, it is true. But as you're saying, it should not be true for larger. So, well, the easiest way to do it is maybe to just check for f3. f3 is 2. And you can check this. Is this, but it will be a little work to be done to check. I don't know. You have to check. So take this as a homework and think. Yeah, maybe you can find some n for which this fails, or find some reason to show that this is not true. Right? This can be a good thing to think about, since I've already spent time on other versions of this question. Try this. Okay? So you can go with the calculations. You can go to f4, f5, and see if you can find somewhere where it fails is good enough, or you think of something else. I don't know. Right? So you have to think. Right. So then, yeah, try the other questions in this. Yeah, especially the ones with a Fibonacci related, like 3.6.1, 3.6.2. Try them. And yeah, even in between the days, you can, because there's some gap, so you can, yeah, ask me, send me a mail or something like that. Yeah, if you need to. Okay. All right. So it's good that you worked, and I think this is what we should do more of, right? Work out the things, actually work them out in the details. And then we see. Soon on, we'll get more and more comfortable with this. Okay, thank you.